Hello everyone, welcome to the first edition of De-Stressing Calculus. So, we're doing limits today, and that may sound intimidating, but it really shouldn't be. So, first off, what is a limit? Well, a limit is this. The limit as x approaches a, it's read the limit of f of x as x approaches a is equal to L. That looks a bit intimidating, but let's just break it down. It's really not that bad. Just ignore this little blob about what to do. This might look scary. Don't worry about it. It's really not. What the limit says is that as x approaches a, this value right here, well, the closer and closer you get to a, which is this delta value, the smaller this delta value gets. So the closer you get to a, the closer that your epsilon value right here will get to L. So essentially, as you approach a from the right, you're going to get to here. As you approach a from the left, you're also going to get to here. So it's useful for something like, just think of the function 1 over x. You know how that's got the asymptote? Well, you can use that to figure out what it would hit at 0 if there wasn't the asymptote. And by that, I don't mean, like, figure out, like, if it just kept going straight. I mean that, like, you would figure out what it would hit the asymptote at, which ends up being, well, I won't get into that. So over here, we've got this function, which is the limit as x approaches a of f of x. So it's essentially as this little plus sign, which you may or may not be able to see. That plus means from the right, and minus means from the left, which makes sense. Plus positive, minus negative. That's how math works. So what that means is as you approach a, which in our case is 3. So as you approach 3 from the right, you're getting closer and closer and closer to this value right here, which is 2. As you approach from the left, you're going to get closer, 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 and you're also going to hit 2. Now, be warned, you're not actually going to hit that point right there. Like your delta value, which is this thing right here, is going to get infinitely small so that you're essentially hitting that spot. So if you look at somewhere like over here, as you come in from the right, you're going to get to here, but as you come in from the left, you're going to get to here. It doesn't matter that the point's actually up here. So over here, you can see it since you're getting closer and closer and closer from the right, and it's 2, and closer and closer and closer from the left, and it's also 2. Since they're the same number, because 2 is the same as 2, then the limit as x approaches 3 is 2. So essentially, the limit of f of x as x approaches a from the right, if that is not the same as if you were to approach from the left, then the limit does not exist. It's so essentially right here, as you can see, you approach 3 from the right, and you get 7 way up here. But if you approach from the left, you get 5. Even though the actual point is at 7, since 7 does not equal 5, the limit does not exist. But if you were to plug in f of 3, you would get 7. So limits don't necessarily have to exist, even if that point does exist. Now, that's how you look at them graphically, and that's pretty nice. I mean, it's rather convenient. They're not that scary. If they are scary, don't worry. I'll get you through this. But you can also look at them algebraically, which is rather nice. And, well, what do? Well, you rearrange it so that by plugging in, you will not result in a zero denominator, because we all know that that causes black holes. And then you just plug in a, and then the resulting number is L, which is that value right there. So that's rather convenient. So over here, for example, the limit as x approaches, or the limit of x plus 3 as x approaches 0, well, you can just plug in 0 there because you're not going to get 0 in the denominator. So you get 0 plus 3, which is 3. So that was pretty easy. Well, what happens if you get 0 in the denominator? Well, in this case, the limit of this function is x approaches negative 4. If you were to plug a negative 4 in the denominator, you're going to get 0, and that is not good. So, you can just factor the top, and I think it's factor theorem. I forget which one it is. But essentially, you know, if box cubed plus triangle cubed, then box plus triangle times quantity of box squared minus triangle box plus triangle squared. So you get x plus 4 times x squared minus 4x plus 16. And the x plus 4's cross out. then you get x squared minus 4x plus 16, and suddenly you can plug negative 4 into it without getting 0 in the denominator, and you get 16 minus 16 plus 16, which is just 16. So you can see just by rearranging, you can get something that doesn't give you 0 in the denominator. In this way, we just use factoring. And another way that you could use it is in this problem, the limit of x minus 9 over the root x minus 3. We actually multiply it by the conjugate of the denominator. And the reason why I do that is because when you multiply it all out, you get something that, again, allows you to cross out these numbers. That's really the goal in all of this. It's not to move something around, it's to make so that you can cross it out. So you either factor it right away, or you just multiply the conjugate. So here, we multiply it by root x plus 3 over root x plus 3. You get x minus 9 times root x plus 3 all over x minus 9. These two cross out, and you get the... Oh, make sure that you keep this limit notation. You can't make that disappear. If that goes away, you instantly fail. It's no second chances. It's all over. So then you get the limit of root x plus 3 as x approaches 9. You can plug in the 9, and you end up getting 6. So there we go. We've had a relatively stress-free introduction to limits. If you're interested in the formal definition of limits, well, here you go. This right here is the formal definition of a limit. Now, what does that mean? Well, this essentially means that for your f of x, as you get closer and closer to a, you're going to get the cell value. As long as, well, if for every epsilon greater than 0, there is a delta greater than 0. And what does that mean? Well, that means that, such that 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus l is less than delta. So essentially what this is meaning, this whole definition up here is, for every positive epsilon you get a positive delta. That means that right here, it all comes back to this one right here. This is super important. As your delta and delta get smaller, that means that your epsilon gets smaller. So for every epsilon out there, there exists a delta. So what I'm going to end up doing is eventually you'll get to a point where someone's going to tell you, hey, I want to get this close to L, and they'll give you the epsilon, and you have to be able to chuck back this delta right at them and say, hey, this is my delta, and it works, and show them that it works. I probably won't get to that with you guys because it's kind of annoying, but that's essentially what the formal definition means. It looks scary, but really all it means is as you get closer to L, you're going to get closer to A. The delta, as your epsilon gets smaller, your delta will get smaller. For every epsilon, there exists a delta. Well, there you go. Hopefully that was de-stressful. Stay tuned for the next parts, which hopefully will also be stressful because there's no crying in calculus. Together, we can get through this. I will hold your hand and walk you through it if needed. So, thank you. Check out other videos, like, subscribe, comment, favorite, do whatever you want. Have a wonderful day.